All right, so now we are going to move on to the important subject of basis vectors. That is the basis vectors that we always have been talking about, the orthonormal basis vectors of our Ket space, and ergo the bra space by duality. The relationship between basis vectors, Hermitian operators, and the postulates of quantum mechanics, which really ties all of this together. So this is a really critical lesson for understanding sort of the core formalism of quantum mechanics, but we're not going to solve any big problems with it since this is all about formalism. Okay, so let's begin. We know that, let's quickly dispense with Hermitian operators, right? Because we know that any operator acting on a state that we're going to label with lambda is dual to the Hermitian adjoint acting on the bra lambda. That is the definition of the Hermitian adjoint, right? This is the definition. And this relationship is dual correspondence, right? Dual correspondence, right? That's how that works. And without, going into detail, we're talking about the vector space here, and we're talking about the dual space here. So this is the dual space of bras and the vector space of Kets. And presumably our physical states live over here. So now, with this dual correspondence, we can do a quick analysis. I can, for example, take this Ket and find its inner product with the state gamma, right? With the way I'm now reverting to the quantum mechanical language, the inner product of this Ket, that is the transformed lambda with the bra gamma, which is the inner product. So I just say inner product. Now notice we've chosen to call this the transformed lambda, right? We could have easily just as said, oh, we're going to transform the bra, because operators can act in both directions. Don't think that Hermitian adjoints can only act this way and non-Hermitian adjoints can only act that way, because remember, A hat Hermitian adjoint, well, that's A, right? So this is a matter just of taste, but it is irrelevant, right? The point is that when you see something like this, an operator sandwiched between a bra and a Ket, you can think of it's still just, in the end, an inner product of a single bra with a single Ket. It just so happens that the Ket B has been defined as A hat lambda, right? This is a transformed Ket, so it's got some name. Well, let's call it B, and now you're back into this territory. But regardless, you can multiply. Well, multiply is probably not a good word to use for this, right? Multiply by the bra on the left. As long as you understand what that means, you could define this as some sort of multiplication, I suppose. But the point is, you're going to take the inner product with the state gamma. Likewise, over here, you've got this bra. You're going to take its inner product with the state lambda. A little easier to understand because perhaps the vector space contains the physical state. So as a Ket, gamma, the state gamma is in fact a physical state. Or here it's the dual, but we don't highlight that. We still say inner product with the state gamma. So you can do it on both sides. Now, are these two things equal? Well, what would we have over here? We would have gamma times a Ket we called B. And by definition, we know that this is the dual of B, right? So we have B gamma. And we know the rule is that when you flop the two bras and Kets around, right? When you flop these two around, you have to take the complex conjugate, right? So those two are not equal. They are differing by a complex conjugate. So I have to go equal, but I have to throw in the complex conjugate. And that's cool. Right now, what you can see is that these two are equal. This and this is being equal tells us that the matrix element of the adjoint is the transpose, where you flop, where transpose is defined in this case of flopping the bra and Kets. It's the transpose conjugate of the matrix element of the operator A. So if we chose a basis, say we chose a basis which we're going to call I over here for this vector space. Let me clean that up. Right, so now we've got our vector space of physical states called the Ket space, and we have the basis, the orthonormal basis I. If we replaced gamma and lambda with basis vectors, we would write something like I, A, J like that equals J, A adjoint I, and this we would literally define as a matrix element Ij, right? And this we would literally define as the adjoint matrix element conjugate, Ji conjugate. And then I could maneuver this to say Aj conjugate equals adjoint Ij. And this is where the relationship where we say the Hermitian adjoint is the conjugate transpose of the Hermitian adjoint of an operator is the operator's conjugate transpose. It's when you cast it as a matrix. And if you go through most quantum mechanics books, they actually do this. They actually take the time to create the matrix for the operator A. And they take all kets, right? A ket, say some ket A, and they break it down into, A1, 1 plus A2, 2, and then they turn this thing into a column vector, and then they show that the associated dual, right, A1 star plus A2 star, etc., that the dual conjugate, right, which is the bra of A, right, that's what this is, right, they show you that this is a row vector, and then they show you how all of this is literally matrix multiplication. And it is. It is. The problem, of course, is that the matrices and the vectors are infinite dimensional, discrete infinite dimensional. And eventually we're going to talk about basis vectors that are infinite dimensional and not even discrete. They're going to be continuously infinite dimensional. So this matrix thing, to me, is always a bit of a kludge. But it does work, and it is literal. In general relativity, you don't have that. You can't turn the vector spaces and the operators and the metric in particular. You want to stay away from that matrix type analysis in general relativity. In my opinion, you don't want to you don't even want to use it as an analogy. In quantum mechanics, it's so literal that it's a great analogy, right? It works really well, except for the fact of the infinite dimensionality, and it doesn't work at all when you have continuous. A continuous basis, which we have to talk about because that is unusual. Anyway, this is the point about the definition of a Hermitian operator, right? About the definition of the Hermitian adjoint. Now the question is, well, what does it take to be a Hermitian operator? Well, the definition of a Hermitian operator is the operator equals its own adjoint. So it has to be that the transpose of every element must be the conjugate of that element. So it must be that, say, A12 must equal A21 conjugate, right? So every position in the associated matrix for A, I guess this is A12 here. So this has to be A12 conjugate down here, right? Normally that is the slot for A21. So A21 equals A12 conjugate. And that has to be true for everything. And the diagonal elements have to be real, right? Because that would be A11 equals A11 conjugate, because the transpose of a diagonal element doesn't change. But the only time you can equal your own conjugate is if you're real. So the diagonal elements are real. The off-diagonal elements are related by conjugation. So that's the definition of a Hermitian operator, right? It is equal to its own conjugate. So if you were to go through this, you could make some adjustments, right? First of all, you could get rid of that, right? And you could get rid of that, right? And you could get rid of that, and you could get rid of that, right? So everywhere you saw a little adjoint, you would get rid of it, right? And then you get rid of it here. Whoops. Let me erase it there. Erase. Erase it there, and that goes back to where we were a moment ago, right? So that's the definition of a Hermitian operator, as it equals itself. Now, given a Hermitian operator, we should be able to run through a very basic proof that everybody should know, because it is such at the heart of quantum mechanics that this is a really simple proof, and it's critical to the theory. All right, step one is we're going to take an operator A, which is presumed to be Hermitian, right? So A equals its own Hermitian adjoint, right? And we're going to find a particular vector in the vector space such that when A transforms this vector, it really returns the same vector, right? It doesn't return a different vector. It returns the same vector. Now, keep in mind that in the vector space V of physical states, right, of physical state, it's a complex vector space. A vector in this physical space is actually just one point in the set, one element of the set of the vector space. However, a physical state is a ray in the vector space. And the reason that what this means is a ray in the vector space means that if I take any vector v, its ray is some complex number times v, and I can put in any complex number there. And that would be a ray in this vector space. And the point is, a physical space state is really represented by a ray. So any element of the vector space that looks like some complex number times lambda, this is actually the same physical state as represented by lambda. It's the same. Lambda is the ket is the critical state in question, is the state in question. So any complex number times the ket is still the same physical state. So that's why I can say that A times lambda, it returns the same physical state, but it returns it with some complex number scaled by some complex number, and that complex number will be lambda. Now, this is a normal convention. If this is the case, right, if we're talking about a state that is unchanged by an operator, we give the state the name of the complex number that scales the state through the operation, right? So, for example, if this was simply the case, we would literally call this guy I guess I should just say it, right? This is called the eigenvalue. This is all a review, I hope. Value. The lambda is the eigenvalue, and this is the associated eigenvector or eigenket. And it's given the name of it's given a name of the eigenvalue. And somehow we know that this ket is an eigenvector of this particular operator A, right? You could throw in a letter A here as some sort of indicator. That's not typically done. Usually the problem is so contextual that you know, okay, I'm dealing with the eigenvectors of A. Certainly if you see this statement, you know right away, because that's literally an eigenvalue equation, right? So operators have these eigenvectors, and these eigenvectors all have these eigenvalues, and that's a lot of material from elementary quantum mechanics. No course does without that. All right, and so, but all we want to do is in the formalism of the Dirac formalism, we want to show this quick and important fact about Hermitian operators, their eigenvalues, and their eigenkets. So we're going to start by taking the eigenket given by lambda prime, and this is, by definition, the relationship. We're just presuming we know what these eigenkets are, right? And by just abstract definition, this is in the operator formalism of Dirac notation, this is an eigenket of A, just because you see it laid out in this fashion as an eigenvalue equation. Oh, I'm missing a prime here, right? Let me put that prime in. So this is one eigenket, lambda prime. Now we go to another eigenbra, lambda double prime. And it's really, it's just the dual of the eigenket lambda double prime, right? So it's the dual correspondent to the eigenket lambda prime. But A operating on lambda double prime is dual to A, well, let me just do it this way, right? It's dual to A operating on the ket lambda double prime. Well, the ket lambda double prime is lambda double prime like this. What's the dual of this thing? Well, the dual of this thing is lambda double prime bar bra corresponding to lambda double prime. So that's why, so don't get confused. That's why that complex conjugate comes up. A lot of people, when they do this, they forget that, it's its own, A is its own Hermitian adjoint, but the rule of dual correspondence still pulls out this complex conjugate. You can't get away from that. All right. So now we do this. So we've identified two different, well, I shouldn't say we have identified, right? Because it's not like this abstract operator A has a lot for us to work with, right? It's not like we've discovered. We've asserted two separate eigenkets, the eigenket lambda prime and the eigenket lambda double prime. And we've worked the two eigenvalue equations, one in the ket form and one in the bra form. All right. So the next step is to simply create inner products for both of these that yield the same numbers, right? So what we're going to do is, I'll do this in red, that in the ket equation, I'm going to take the inner product with the eigenket lambda double prime on both sides, right? So I guess what I'll have to do is move this over a little bit and then squeeze that in lambda double prime like that. And then on this side, I'll do it with lambda prime, the ket lambda prime, which is really a little easier to squeeze in. And then what do I have now? Well, this is a complex number. It's the inner product of lambda prime and lambda double prime. This is the same inner product, right? These two are the exact same inner products. And this is the inner product of the ket A acting on lambda prime and the ket A acting on lambda prime with lambda double prime. So this side's the same. So I'm going to subtract the bottom from the top, right? So on the left side we get, I'll do this in blue, on the left side we get 0, and on the right side we get lambda prime minus lambda prime minus lambda double prime conjugate, and then the inner product of lambda double prime, lambda prime, right? So this is the critical equation. It teaches us two really, really important things. First of all, if we take the further assumption that lambda prime does not equal lambda double prime, right? Lambda prime does not equal lambda double prime. We don't know anything about this, the inner product of two lambdas that do not equal each other, right? But we do know something about this. If lambda prime does not equal lambda double prime, this guy is not equal to 0, right? But notice the left-hand side is 0. So right away we know that two eigenkets, well, the punchline being that this therefore must be 0. I started by saying we don't know anything about this, but we know something about this. It's not 0. But now we know that if this is not 0, in order for this equation to be satisfied, this must be 0. And that immediately tells us that the eigenkets of a Hermitian operator are orthogonal, right? That is really, really important. The eigenkets of a Hermitian operator are orthogonal. Okay, well-known fact, but here it is in the Dirac notation. And then, but we're not done, because we could assume that lambda prime did in fact equal lambda double prime, right? And if that was the case, then this guy would not be 0, right? The only way an inner product can be 0 is if one of the two are 0. And if they're both the same thing, and we presume that these are not, neither one of these are 0, this cannot be 0, and this must be 0, right? So if you get lambda prime minus lambda prime conjugate equals 0, for the circumstance where the lambda prime and lambda double prime are the same, I just made the substitution. Well, the only way a number minus its complex conjugate can be 0 is if the number is real, right? So that brings us to our second critical point. That is, the eigenvalues of a Hermitian operator are real. Okay, so these two statements, they are the statements that are going to allow us to actually apply physical structure to our vector space. See, every time we create our vector space of physical states, you've seen me how many times say, well, we pick a basis, and the basis will be orthonormal, right? Orthonormal. And the presumption that we can do this, I mean, vector spaces have bases. I think we actually proved this in in the Foundations of Quantum Mechanics lecture series that I started. All vector spaces have a basis, even the infinite dimensional ones. You got to kind of lean on the axiom of choice a bit to get that all nailed down. But the point is how do you choose one in such an abstract construction? How do you actually choose an orthonormal basis? And so now we're going to now allow the physics is going to choose the basis for us. So actually the way I should say this, and you'll see why in a moment, the physics tells us what basis we can choose. Then humans choose. So humans choose the basis, and the physics tells us what basis to choose. Now, this is a little different from general relativity. You may remember in general relativity, we talked about the metric of space-time. And the metric of space-time told us about the connection, the connection on the space-time. And the connection of space-time told us about the geometry, right? And we allowed the physics to give us the metric through the Einstein equation. And then everything flowed from there. In quantum mechanics, it's a little bit different. The physics tells us all the different bases we could choose for our vector space. The point is you, the experimenter, the scientist, actually kind of has to make the choice. And this is sort of a fundamental distinction between classical mechanics, where physics drives everything, and quantum mechanics, where physics sort of gives us the arena, but we kind of have to choose how we want to enter that arena. I won't get into the philosophy of it all right now, but it is very interesting. What we're now going to do is we're now going to go look at the postulates of quantum mechanics, and we're going to see why these two statements are so important. All right, so let's see if I missed anything. No, let's move on. So I found these postulates on Wikipedia. They're the best ones for our purpose because they sit in the Dirac formalism. They're all the Dirac formalism. You don't see any wave functions in this. Although I will point out, you see these guys down here, which we will see look very similar to wave functions. So there are many different versions of the postulates. Every book is different. There's no international standard on what the postulates of quantum mechanics are. But they all kind of get at the same points, and the variability is interesting. It's actually kind of interesting to compare the different postulates. I actually wrote down some of them from other books, but I don't think I'm going to use them. I'm going to use these from Wikipedia. So the first postulate we talked about in the first few lectures, which was the state of an isolated physical system is represented at fixed time by a state vector. So they're very, it's interesting the things that they're worried about. They're worried about, isolated, because they're very concerned that, quantum mechanics doesn't look the same when you connect it to the environment. It becomes a bit more of a complicated story. So we really want to say if we're dealing with a state vector that has any persistence in time, you kind of need to keep this thing isolated, because as soon as you connect with the environment, any state vector is going to start collapsing on you, which is another postulate. But that aside, they're interested in at a fixed time t, because that's a signal to us that state vectors change in time. Right? We haven't discussed this, but we name a state vector phi. There's really phi at a certain time, and at a later time, this becomes a different state vector. We can still call it phi, but we got to give it its new time stamp. And the question is, well, how does that happen? If we know what we're starting with, how do we end up with something new? And that, of course, is postulate 5, right? The time evolution of a state vector is governed by the Schrodinger equation. So postulate 1 starts with the fixed time, because later they know they're going to say, oh, this is how it evolves in time. Now, we already quibbled a little bit about state vector representing a physical state, because it really is a ray, right? So you could actually quibble about this postulate, that they're not really jumping on the fact that a physical state is represented by a ray in Hilbert space. But that is a bit of a quibble. And here they also introduce the concept of a Hilbert space, which technically is an inner product space that is complete, right? So it's a bit of a topological name, or it's a name that talks about the topology of the vector space, but it does demand that you have an inner product. If you see the word Hilbert space, you know you've got an inner product, which is critical. I mean, we've already seen the whole Bra-Ket formalism depends on having a Bra version of every Ket, and you can only do that with an inner product, and a Hilbert space has an inner product. Okay, so we've already kind of dispensed with postulate 1. It's postulate 2 and 3 that we're really beginning to talk about today. And we've already talked about Hermitian operators, but here they show up as postulates in quantum mechanics. Every measurable physical quantity, right? A lot of philosophy in there, right? The quantity A there's a Hermitian operator associated with each measurable physical quantity. That operator acts on the state space H, which is the state space of Kets, right? This is our Ket space. So the first thing is, well, wait, measurable physical quantity, that's the stuff that we can check out in a lab. And we're going to associate with that a Hermitian operator. And this is done by a postulate. I don't have to prove this. Right? 30 years of development of quantum mechanics, they've come up with this as the model. And postulates, by the way, it's not unique to quantum mechanics. We kind of lay them out in quantum mechanics, I think because at some point they realized this stuff is so hard to teach that instead of really working our way through these facts, why don't we just stipulate them at the beginning, force the newbies to accept them, and then allow them to kind of go back and figure out why they might be true afterwards. We just got to get the theory into their heads first as we've created it, and then they can go back and work on understanding why these postulates might be valid. So we're going to kind of explore a little bit of that right now. So the next part is we're going to call these Hermitian operators observables, right? So we give a definition of that. And then they say to be an observable means that your eigenvectors form a basis for the state space. And that's really interesting because we know that the eigenvectors are orthogonal, right? Right? Now, discrete spectrum eigenvectors we'll write as orthogonality as delta ij, with the possibility that it's not normalized, so there might be some constant out here, so it doesn't necessarily equal the delta function. We'll talk about normalization in a moment, but so it is true that the eigenvectors of H are convenient for a basis. A basis does not have to be orthogonal. Right? You can have a non-orthogonal basis where I with j does not equal 0 unless I equals j. That is possible, but it is always convenient to have a nice orthogonal basis. So it is true that we now know Hermitian operators, the eigenvalues would certainly be nice for a basis because they're orthogonal. The problem is, are they complete, right? Do they span the Ket space, right? Because if you don't span the Ket space, you can't be a basis. Well, the fact that they span the Ket space is considered a postulate, right? Now you can kind of prove this for finite dimensional vector spaces. You can prove this stuff. You can actually, in principle, even prove it for the infinite dimensional vector spaces using a very, I want to say, esoteric analysis that involves ideas called the Gelfand triples and rigged Hilbert spaces and other things, and the nuclear spectral theorem. Actually, I think I've confused different issues, right? These two things are important to show. Yeah, it's all related, actually. But the nuclear spectral theorem, these are very complicated ideas of very arcane forms of linear algebra. However, it's nobody ever studies that stuff, right? Nobody who studies quantum mechanics at a functional level, right? Certainly at a introductory graduate or certainly at an undergraduate level works on that. We just go with the postulate that if you're an observable, meaning you're a Hermitian operator associated with a measurable physical quantity, the eigenvectors of that observable form this basis. And that's good. I mean, at least we are guaranteed orthonormality straight up. We're guaranteed orthogonality straight up. We're also guaranteed orthonormality too, but we'll talk about that hopefully later. So postulate 3 is kind of what motivates that a little bit, is the result of measuring a physical quantity must be one of the eigenvalues of the observable, right? So when we measure something, right, this is the whole this is the binding of these two. If something is measurable, it's got to be real. And the only way our theory now so far can produce, the things we've constructed are operators and state kets, right? And the only way we know how to get a real number out of that is if we have a Hermitian operator acting on an eigenket, we get a real eigenvalue. So if we want our measurable quantities to be real, we got to figure out a way for our theory to produce real numbers. And you could say, well, our theory has plenty of complex numbers, and for every complex number, you just take its modulus, and that's real, right? But that just means every possible thing. It's too blunt, right? Everything becomes eligible to be a real number at that case. The theory doesn't have much value. It's this delicate way of producing a real number, which is where our physics is going to show up. And so now so finding real numbers gives us postulate 3. Perhaps they would say, well, how are we going to get real numbers out of this? Well, eigenvalues of observables. Well, now we say, if you're measurable, you must be the eigenvalue of some observable. Okay? So now postulate 2 and postulate 3 together kind of really lean on everything we can measure is a Hermitian operator. So, all right, what else? Well, let's see. Postulate 4, this is just Born's rule. We won't bother you with Born's rule. This is, if you don't know how Born's rule works, then we're going to go over how this is all done in the Dirac formulation. But obviously, once you express your state in a basis, you can calculate the probability of a certain measurement. That's elementary quantum mechanics. Postulate 5 is the one which kind of ties these two guys together a little bit. In other words, we have a complete... It's not totally obvious why an observable's eigenvectors must form a basis for H, and why a measurement must be an eigenvalue. It's not completely tied together, but postulate 5, which is the one that gives everybody heartburn, which is really the collapse postulate, right? That basically says after you make a measurement, you leave your state in an eigenstate. And this is what gives us the foundation, really, for saying that a state gamma can be represented as gamma 1 basis state 1 plus gamma 2 basis state 2. It can be expanded, right, in eigenstates. These are now eigenstates of some operator A, right? And we know that if we have eigenstates of an operator A, we can take it forms a basis of the space, right? It forms a basis for the quantum mechanical space. Ergo, I can take any physical state and I can expand it in this basis. And after the measurement, it's going to collapse. This state is going to disappear, and one of these states is going to take over and become the new condition of our particle. And the probability for that to happen is, of course, related to the component, right? That's Born's rule. But the collapse is what says you land in one of these states. And between the fact that you collapse to a state, measure with an eigenvalue, that tells you that every state can be represented. That's the next part of the postulate system, is really that every state can be broken up into these eigenstates, which is what this is. It's a basis. The eigenstates are a basis for H. So these three kind of bind together this whole principle. The last postulate, by the way, is this is the Schrodinger equation. Many books don't even include this as a postulate. They say, oh, we're smart enough, we can derive the Schrodinger equation from first principles. That's debatable, right? Depends on what you consider first principles, and is there a hidden assumption in there. By the way, general relativity is another example of a theory that has postulates, right? In general relativity, the postulate is, oh, I can model space-time as a four-dimensional Lorentzian manifold, right? Or locally Lorentzian manifold with a metric, right? You write that stuff down, right? That's a postulate of the theory, right? That's you don't have, that's motivated by hope, right? And then you create a theory, and if the theory works, you win, right? That's what they did with quantum mechanics for 30 years, and this is what they came up with. Okay, so to sum up the significance is the postulates tell us that these special observables are, these special things called observables are associated with measurable physical quantities. The theory only talks about measurable physical quantities. We give up everything else. And the way the theory now is you find these measurable physical quantities, you create their operators, you assert their basis vectors, or you assert their eigenvectors, and then if you choose, you can now make a basis of your state space, and using those eigenvectors of these operators. Now, there's a lot of subtleties here, right? There's stuff about degenerate eigenvalues, right? You can have different eigenkets with the same eigenvalue. You've got to be able to clean that up, and all the elementary quantum mechanics courses have done that. We're not going to reproduce that work. I kind of want to get a bit more formalistic and foundational. That's the prerequisite I think is relevant. If you don't know quantum mechanics in its elementary form, then yes, you've got to go review it. This is more like, this is the kind of stuff the kind of conversation that's been a little bit that you know, you spent so much time solving differential equations and diagonalizing matrices. It's time to go back and sort of look at the fundamentals a little bit. Okay, so what's next? So the last thing I want to cover before we close is, let's consider an operator and its eigenkets are given by this lambda. We now know that these guys are orthogonal, but we're going to further presume that they're orthonormal, right? That you can scale these guys with some complex number. Remember, you don't change the physical state by multiplying by a complex number, but you can scale these such that you end up with this delta function orthonormal relationship. And this is true if you have a discrete spectrum, right? That means you have a countable number of lambda. You have lambda prime, lambda double prime, lambda triple prime, lambda quadruple prime, etc. If you have a discrete spectrum, this is how you normalize them. Now, there are some operators that do not have a discrete spectrum, or there are some circumstances where you have an operator that has a discrete spectrum sometimes and a continuous spectrum other times. But the classic non-discrete spectrum is the position, right? The position of a particle in principle can be anywhere on the real line. So position is measurable. It must be represented by a Hermitian operator. That Hermitian operator must, by definition, operate this way. Look how abstract that is, right? The postulates tell me if it's observable, there's a Hermitian operator. So I say, okay, x is an observable. The position in the x direction is observable. Ergo, it must have a Hermitian operator. Ergo, it must have eigenkets, and those eigenkets are going to be written with the eigenvalue, and that eigenvalue will be the result of the measurement, which is x, right? Straight up postulated, right? The problem, of course, is if you have continuous spectrum, then you really can't do this, right? Because x prime and x can never really equal each other. So now you start working with this notion of the Dirac delta function, right? X prime minus x double prime. And this is for a continuous spectrum. But this counts as normalization, right? This is the normalization of the discrete kets, and this is the Dirac delta normalization of continuous kets. And they count as normalized. So, and the same rule applies. You just scale these things until you get this normalization. We'll talk a little bit more about this in our next lecture, where we're really going to dig into the nature of these continuous versus discrete issues. An example of and I'll give in that next lesson an example of a circumstance of an operator that sometimes is discrete and sometimes is continuous. Okay, so that's all for today.